Okay, welcome back to the second half of morning session. It's a pleasure to introduce Mariusz Tobolski, who will tell us about contravariant functoriality for graph algebra.
Thank you very much, Jack, for the introduction. I'd like to thank the organizers for inviting me. Giving a talk at a conference is always exciting, but also stressful because you have to prepare. First, you have to think about what you want to talk about. Then you have to prepare the abstract and the title. But it wasn't that stressful this time because Piotr just came to me and you said, he will talk about this and this. This is your title. This is your abstract. So if you have any complaints about my talk, direct them to Piotr. And this is a talk I already given at the North Atlantic Non-Commuted Geometry Seminar. So I'm sorry to those who already heard this talk. I wanted to change some things, but then I liked this talk so much I didn't change a thing. So I'll talk about contravariant functoriality of graph algebras. So Piotr was talking a little bit about this, and I'll give you more details. I'll not talk about covariant things at all. Right, and this picture that you have here, this is the first motivating example I'll be talking about. So I'll give you the details just in a second, but I just wanted to say that I already on my first slide I have 4 graphs, so the ratio of graphs per slide is very high right now. We'll see how it goes. Okay, so I want to start with motivation for this, and the motivation, just like for Piotr, because this is joint work with Piotr, by the way. I didn't know if I mentioned that. It's here. So we had this motivation coming from non-commutative topology. And examples coming from non-commutative topology. Oh. And the main example is the equatorial Podley sphere. So by this I mean the equatorial. And if you look already in the, probably already in the Podley thesis, that's what at least what Piotr is telling me. I never saw the thesis, but you had this pullback diagram of all maps surjective, pullback diagram of C-star algebras. Where here, this is the Tobolski algebra. And we have the symbol map. So the map that Elmar was talking about in Piotr is a very famous map used in index theory. And here as well. Right, so this is a pullback. And that was proven already by Podlej and then independently by Albert Schuh. Again, this is you get this picture, this kind of a CW complex picture of a sphere. So you get a sphere. Oh, this is done. So the pictures is as follows. You take 2 disks, right, and you glue them over the boundary circle. Right, so the circle as a boundary of a disk, and then you glue it this way. And this is the non-commutative manifestation of the CW complex structure, this pullback diagram. Okay, and so this is interesting from the point of view of non-commutative topology. But then, if you go to graph algebras, because Hong and Szymański, also a paper that was cited many times for this conference already. That's the one in 2002 about quantum spheres. So they observed that this algebra has a graph attached to it, so it's a graph C-star algebra. It was already known that Tobolski algebra and this one is a graph C-star algebra. So we can draw this. right? So you have your equatorial Podlej sphere and the graph of the Tobolski algebra. And what we did with Piotr, we just drew those pictures and we were looking at it, astounded because it looked like push out, right? But for graphs now. So it was kind of mind-boggling because, okay, so on one hand, we have a push out here, this on the topological side, and it turns into a pullback via the Gelfand-Naimark duality, right? And then you Q-deform the picture and you get what is here. But how on earth push-outs of graphs give you pullbacks of graph C-star algebras in the same way? So we wanted to understand this. What is the what's the principle behind this? Right. So this was our question. Oops. The question was when do push-outs of graphs induce pullbacks? Of graph C-star. Okay, I didn't tell you what a push-out is, and if you look at this picture, right, I didn't say what do I mean by a push-out, but just looking at this at the pictures, you know what I'm talking about, right? I'm just gluing this part, right? I'm gluing over this part, those two guys, and then how I put the two legs. I'll be more precise in a second or during the talk. Anyway, so this is the question. This is the thing we wanted to do. And before I will present you what we proved with Piotr, I'll talk about previous results because so you can see the progress. Oh, thank you. Looking for this. So first, of course, the first progress was the paper of Hong, Szymański, and this picture from my first slide. But then Hong and Szymański, they had a follow-up paper. That's 2008, and that was about quantum balls now, when they did the same thing as for the Podlej sphere, but now for any even-dimensional quantum sphere. And they defined those quantum spheres as some quotients of even quantum spheres, and the even quantum spheres are the Waxman-Soibel quantum spheres that Francesca was talking about, and Francesca as well. So, so that was the first result. Then you generalize it to higher dimensional spheres. So you had it for Podlej. Now, then there was a paper that we first kind of missed by Robertson and Szymański, and that's 2011. And it was pointed to us by a referee for a different paper, by the way. So, and they were dealing with Kunz-Pimsner algebras. I won't define Kunz-Pimsner algebras, but this is just a review of the literature. However, I can tell you what happened in their paper is that they had some, but their result was kind of covariant, because from correspondences, from pullback of correspondences, they got the pullback of Kunz-Pimsner algebras. Okay, but if you look closely at the result, and you look at the correspondences and the conditions they had of the Kunz-Pimsner algebras, what they were doing actually was just working at the level of graph C-star algebras. Okay, so graph correspondences, they were working with row finite graphs and two injective push-outs or two surjective pullbacks. So that was a vast generalization coming from spheres to here, and we were not aware of that with Piotr at first, and we had two papers with Atabey and Kaigun, and with Sarah Ryzhenkov. That's 2018, I guess. So we had two results, and they were about our first attempt was also we deal with row finite graphs and two surjective pullbacks or two injective pushouts, depending on from which perspective you're looking at this. And but our result was, you could very easily generalize it, and this is what we did very quickly, that you can do arbitrary graphs. But without breaking vertices. But I was very sloppy on our side. And if you write a paper and you're sloppy, you're almost sure that someone will just come there and write a paper and just clean up your mess. That's what happened. And Sambrucker and Jack Spielberg, they wrote a paper. That's a very recent one. And they were dealing with Tobolski algebras, the ones that Alex Frank was not, I guess not here, was talking about doing Piotr-Stock. So completions of compact algebras. So they were dealing mostly with Tobolski graph algebras and relative Tobolski graph algebras. But if you do if you kind of restrict to the special case of graph system algebras, they dealt with those breaking vertices. So they added breaking vertices. However, let me emphasize that all results are for two injective push-ups. So what I mean, but intuitively, just to understand what was happening, we were looking at subgraphs. Okay, so we were not so all our like morphisms between graphs were injective because we wanted to embed one graph into another.
Might I make a quick comment?
Sure, please.
It's you see, whenever you have graphs, you can ask a question: does there exist an intersection of graphs? Sometimes it does, sometimes it doesn't. But if the intersection of graphs exists, so does the union of graphs. And then such a two injective push out of graphs is just the union of graphs. That's it. And this is why when you look at this picture of a Podlet generic 1, 2, 3, it's kind of obvious as a push out because you have to tap these graphs and you merge them out of the circle. And it's almost too obvious.
Yeah, exactly. That's why you just look at the picture and you know what's happening. So okay, so that's the past, and now what we did with Piotr and how we generalize all those results. I mean, not all results, like we're not talking about conspiracy algebras or Tobolski algebras, but when you restrict those results to graph algebras, right, we have now something more general than this restriction. And okay. So what we've learned so far from this story. So first of all, what we noticed with Piotr doing all this, proving all those results, and that's the most important part, that this problem, and then I'll do quotation marks, has nothing to do with analysis. Okay, let me explain myself. So what do I mean by this? So what we were doing, we had several proofs for those results, and we were always using Piotr's favorite approach. You start with algebras, so path algebras, build conpath algebras, Levi-path algebras out of that. And we were proving everything for Levi-path algebras. And then, using some arguments, for example, that star homomorphisms are closed and things like that. If you have a pullback and then all the algebras are some dense star subalgebras, then you take those universal involving C-star algebras. We're always able to prove it immediately from the algebraic part to the C-star algebraic part. So the whole problem and the difficulty was at the algebraic level always. Okay, so but we were doing it for every example or for every type of thing. We were doing it over and over again. And then Alex Kivasitu got involved, and he proved a very general results about coming from pullbacks of star algebras and inducing a pullback for C-star envelopes. involving some equivariance. So it's not that for every you can do this. You cannot do this for any completion, for any algebras. For any pullback of algebras, you complete it, you get a pullback. That's not true. But for in many cases it works, and in all the cases that we have to worry about, it works, right? So the whole difficulty of the problem is algebraic. So my talk is purely algebraic.
So it might be worthwhile to emphasize that the completion of the pullback is not the same as the pullback of completions in general. But under some circumstances, it works, and in particular, it works for the theorems, the cases we're interested in.
Exactly. I was just wandering around this statement, and yeah, thank you for making it precise.
You have to nail it down.
Sure. So this is one observation, the most important observation. And the other important observation is that the most general approach is to find a suitable subcategory of graphs. So the thing that Piotr was doing for in the covariant case, I'll be doing for the contravariant case. Oops. Oh no. Okay, so this is our approach. Our approach is just to find a suitable subcategory, and by subcategory, the objects like in Piotr's talk will stay the same. Arbitrary graphs, you can take whatever, but morphisms will be changed. And what I want to emphasize is that in this talk, I'll be dealing with one injective push-outs or one surjective pullbacks. Okay, so this is the first kind of generalization that we want to talk about, and one surjective is for us good enough. We don't want to be more general because we want we are still have to think about non-commutative topology and to have 6-term exact sequences and K-theory and things like that. We want to have one surjective pullbacks. Okay, so this is the approach, and I'll be now going to the main part of my talk. I mean, this talk is very easy to digest, so you have more room for lunch, okay, afterwards. So it will be, hopefully, it will be very easy to digest. So I'll start very slowly, and I'll repeat some of the things that Piotr did, but not too much. Okay, I won't tell you what a graph is. Hopefully, this everyone already got a chance to at some of the talks. My notation would be yes. Right. So this is these are my vertices, and these are my edges and target and source map. Okay, so that's actually the only difference. In my talk during the NCG seminar, I used range instead of target. Yeah. So now, morphisms, I do graph homomorphisms, just like, and part of Piotr's talk was about graph homomorphisms. And let me just very quickly remind you what those are. So a map between two graphs is actually a pair of the theoretic maps. Such that the only additional structure that we have, so the source and target maps, is compatible with. So if I start with the target. I wanted to, because so this is these are two conditions. One is for the source and one is for the target. And they're exactly the same. So So this is the graph morphism, and what is nice about graph morphisms, and Piotr already emphasized this, that it maps edges to edges. So if we will think about now reversing the arrow and looking at graph algebras, it will preserve the grading, it will preserve the gauge action. So these are the morphisms that we get out of this are not only star homomorphism at level of algebras, but they are also equivariant, which is very nice, right? It's different than path homomorphisms. For path homomorphisms, when you don't respect the lengths of paths, then you lose equivariance. And I'll be dealing only with graph homomorphisms. So my morphisms are graph homomorphisms, and now the next slide would be I'm adding some more and more conditions to get a map between C-star algebras. Okay, so far so good. Just so we have it on this slide. So F now is a graph homomorphism between two graphs. Okay, and now I'll be adding some conditions. So the first condition for F to work, for anything that we do to work, is that F has to be proper. And F is proper if both F0 and F1 are finite to 1. Just to be on the safe side, I'll write down what I mean by this. Finite to 1 means that for any vertex, this set is finite. For any vertex E, and for any edge, it's the same. So that's proper, and this we need to even start to talk about morphisms between graph algebras. Now, the next condition is called target bijectivity. So S satisfies the bijectivity condition, and I will abbreviate with TBC. If the following is true for any X now in the pre-image, and for any also for any X and F1. If I take X and F1, and I take the element in the pre-image of X, I take some E, and I map it to its target.
I have a question.
Yep.
I understand that this second condition in the first point,
Mhm.
it is somehow compatible with regularity of some vertices. But what about this first condition?
Oh, it's
Do
just
they assume that pre-image of V is always
fine.
non-empty?
Yes.
Aha. What is?
Oh, maybe. Well, oh, you're right. This is wrong. Thank you, Tom. Yeah.
Okay.
You're right. It can be empty, of course. Yeah. Thanks a lot. Yeah. Because finite to 1 means, well, yeah. Exactly. So finite means empty in particular. Okay. So let me finish this. So are there any other questions? Hopefully. And now, because we're dealing with graph homomorphisms, so we land in the image of target here, and we want this to be bijective for any X. Okay, and so the first map, the properness. So I'll be giving you some spoilers. So properness is needed if you want to have a map for between path algebras. Okay, so that's where you need properness. Then this target bijectivity condition will be needed for the first conscriptor relation, as it's called in the graph C-star algebra literature, right? And now, the last condition will be for the second conscriptive relation. And we say that F is regular if. So I didn't tell you what the regular vertices are, but just bear with me. I'll at least say it out loud, but maybe make sure that I don't have any mistakes here. Yeah, okay. So now regular vertex is not a sink and not an infinite emitter. So anything in between. And then you look at, you say that F is regular if this containment is true. Okay, and this condition is can takes care of the second conscriptive relation. Right. So these are the three condition, and I don't want to write down P, B, C, P, whatever. I'll just call it admissible category of graphs. Okay, so this admissible category objects are arbitrary graphs. I don't put any restrictions on graphs, and morphisms are proper regular graph homomorphisms. Satisfying this target bijectivity condition. Okay, let me give you some examples and then non-examples. So first of all, if you have any F that gives you a subgraph, so it's injective, so it's both injective on vertices and on edges, then injectivity implies properness, of course, 1-to-1 implies 5-to-1. But if your map is bijective, then you get target bijectivity condition, right? If you're bijective for everything, then in particular in this condition here, right, it's satisfied. If you're bijective everywhere, in particular on those subsets. So that's one example, and this is an interesting example as well. This is something. Let me tell this. There was a question about this from the literature. There's this notion of a quotient graph in the literature, graph system algebra literature. I don't like this terminology because it's not a quotient of graphs. It's a subgraph, right? It's at level of C-star algebras. It's a quotient. So people that think only about graph C-star algebras, they call it a quotient. But what's at level graphs, it's just a subgraph. So this quotient graph, it sits in your graph G, and you build it using hereditary and saturated subsets, and those things will satisfy all the conditions, so they will be admissible. Okay, so all those results that we had for subgraphs. So whenever you have a subgraph, then you can reverse the arrows and get a map of looking at algebras. Again, giving you some spoilers, but this is it. So what I'm telling you is that things known from the literature of graph C-star algebras are also morphisms in our sense. Okay, but we are more general because, for example, what we can do, we can be surjective. So we can do this. We can take such a graph and fold it. Right? So so there's this map here. I map this vertex here and those two here, and those two edges to this one edge. Right? This is not an injective map, but it is admissible. Right? So we can check all the things are satisfied with this.
I have a question.
Yep.
Do you have anything on the level of graphs which correspond to ideals?
Yes. So all those
But it's not simply the complement of this quotient. Right?
But this quotient subgraph is how people from graph C-star algebras look at it, right? Is that you build it looking at everything that's outside of this subgraph, right? And this has to be a hereditary saturated subset. And hereditary saturated subsets, they classify all gauge invariant ideals. So every gauge invariant ideal in your graph C-star algebra is classified by some of those subsets, right? So any quotient by a gauge invariant ideal is in this quotient graph thing. But
But in a way, the answer to the question is positive. You look at the complement of the graph. So you have a subgraph and you look at its complement, but you have to specify what you mean by the complement. And the complement means that the set of vertices is hereditary, saturated, whatnot. And you also have to delete all edges that end in this set, which is hereditary, saturated, or whatnot. That's what is meant by complement. And what is, as Mariusz was probably just saying, this is a very beautiful result that when you talk about these gauge invariant ideals, then they are generated by these vertices. That's beautiful. I mean, you just take, this is the generating set of your ideal. This is very strong.
In the row finite case, if the graphs are non-finite, infinite and not row finite, then you have to take care of those breaking vertices.
Yes.
So then it's much more complicated. Like this procedure of
you
don't,
of course
you don't
right,
need.
yes.
If you just delete the arrows, you'll get some nonsense.
Okay.
Yeah. Yes.
But the same principles.
Yes, exactly. Right. So okay. Any other questions? So those quotient graphs are of this type, and then we can do folding, right? So this is what something.
Mariusz, could you write the induced homomorphism? Is what, like putting 2 by 2 matrices into 3 by 3 matrices? In this example.
Yeah, I think so, but I'll have to think about it. I from the top of my head, I know. But you're right. It looks like. Okay, if someone is bored, please just write it down.
It's a homework.
Whenever.
Yeah, it's contravariant. So the induced star homomorphism will go from this graph on the right onto, you will go into the sister algebra on the left. No, that's the direction on the level of graphs. We have a morphism which is gluing edges and gluing vertices. It's not injective. So this means that when you do the opposite map, it's not surjective. And that's okay.
Yep. Okay. Let me give you some non-examples so you don't think that everything is of this type. Very easy counterexample. This is not regular, for example. And I have some. Oh, this is a very important example. This was something that we missed in the first iteration. That if you fold, well, no. So if you fold the way I just told you, so this is okay. But if you fold the other way, so let's say like this. Right? So assume you now fold this way, then this does not satisfy. Okay, so you can fold like this, you cannot fold like this. But this is okay. The only thing is that this new possibility of folding is you don't have to look at only injective things. So the pushouts could be on one hand surjective, but on the other hand injective. So this is something new, and this is another this kind of a generalization that we are looking for, and this way of looking at this from this perspective of finding this subcategory is just gives you the most general answer. I mean, I don't know if that's the most general answer, but gives you the most general answer that we could come up with so far.
Mariusz, may I just make a quick comment? If you look at this left bottom line, this point in the circle graph, I mean, this is amazing. Of course, just as you said, the simple thing is not regular, so you don't have contravariant induction.
Yeah.
On the other hand, of course, you have star homomorphism of the circle sister algebra to complex numbers.
But it's induced by this covariance.
But it's induced by this covariance. So you see, that's why we have to look at this diversity. We have to come up with different scenarios. What we're really after, we want to understand in terms of graphs and combinatorics, star homomorphism. Okay.
Yep.
Sorry, before you change slides,
Sure.
I think this is on. Yeah. So just a reality check for myself in this first example, folding the two edges together. I think the corresponding C-star algebra thing would be 2 by 2 matrices embedding into the direct sum of 2 by 2 matrices.
That's
with
what I
itself.
just talking.
Oh,
Yeah. Okay. Okay.
Yeah. Thank you. Yes.
Yep. Yeah, because you can do this out splitting and get the. Thank you.
So I see some people do homework very fast.
It's much harder to do it when you're giving a talk. I can tell you that. Okay, okay, maybe I'll speed up a little bit. What else do I have? Okay, theorem. That's always nice to have a theorem. So now I want to talk about Levitt path algebras. I will not define Levitt path algebras because Piotr already did that. So for Levitt path algebras, we have this result. This is joint work with Piotr. That if I start with a morphism in the admissible category of graphs, and then the assignments, the following assignments. I start with the vertices. So and this is contravariant, right? So I'll start from F. So F was going from E to F, and now I'll be going from LK. K is any field right now. I'm not talking about star structure for now, and about graph system algebras. So if I start with, and my notation will be different. So Piotr's notation was that he would add chi of W, and I will just write W like from path algebra conventional or the conventional Levitt path algebra book. I hope there'll be no problem with understanding this notation, right? So this we put into these in the pre-image. This is an okay. Okay, I'll be calling this assignment and the map the pullback of that. And I have to do it also for all the generators, right? For edges and for for edges and for edges with a star as well. Okay. Maybe I'm just too fast. I know I'm a millennial, I'm supposed to know about technology, but first time we use this device. So if I take any edge and I want it to use X, you do the exact the same thing over and over again. So this is the most obvious way of doing this.
But now you see why we insist on properness.
Because you want to find sums. Yeah, right. That's your first sanity check, that properness gives you that these are well defined. Because otherwise these are not, you don't know what they are. That. And then for stars, well, you can guess that this is just the same. You can extend this map to the star graph, right? Like in Piotr's talk, and you get this. And you put it in LK of E. And those assignments give rise to a Z-graded algebra homomorphs. Okay, let me now maybe talk about this.
Sorry, is this F bar the same as in Piotr's talk?
Yes. Okay. Thank you. So this is the same F bar. So let me now maybe talk a little bit about this. So first of all, this is a contravariant functor, right? It reverses the arrows for the maps. And with Piotr, we were so used to it from non-commutative geometry that we just reverse the arrows, like not even looking. And from the first time talking with Jack, he was just like, but the natural one is the same way. But for us, the natural one is always the opposite. So this is a theorem that, but it's not if and only if, right? So this is just, we found some conditions that are kind of general, but we don't know if that's all of them. For example, the evaluation map on the circle. Oh, but is it, oh, it has to be Z graded. It has to be, no, but this one is Z graded because it goes from, will be like going from point to point in the circle. I don't know what kind of a map. If you can get this evaluation, we don't know. So this is just one way, but this is very general, and we just found this thing. And now, so okay, so that was the first part and the most important
Mariusz, let me comment. So here, the story is the following. I think it's important to emphasize it because you went straight to the Leavitt path algebras, but the first question which we asked ourselves was, can we use the more general category of path homomorphisms of graphs and induce functor contravariantly? But you immediately bump into the wall already at the Leavitt of path algebras themselves. It's a simple calculation, simple counterexample. You can convince yourself that if your path homomorphism of graphs does not preserve the lengths, then that's it. You can immediately give a counterexample that you have such a homomorphism of graphs. When you follow this recipe, I mean, Mariusz wrote it for Leavitt path algebra, but this formula is identical for path algebras, for cont path algebras, and for Leavitt path algebras. It's exactly the same formula. Only you have to imagine appropriate equivalence classes, in fact, when you write. And for path algebras, there are no equivalence classes. And you already bump into the wall that this natural assignment, this pullback induction is not well defined. I mean, the multiplication which you have in the path algebra is violated if you do not preserve the lengths, which is in big contradistinction to this covariant way. That's why we cannot even think about, things like shrinking the circle to a point. Forget it. I mean, that's it does not preserve the length.
Right. Exactly.
And when you go sort of the opposite way, you say it doesn't fit. So it's not contravariantly induced, but it's obviously covariantly induced.
Yes. Yes. So let me maybe, because you reminded me of something. Let me tell you 2 words about the proof, because so you have a universal Leavitt path algebra is defined as a universal algebra, right? So if you have this assignment, you check if all the relations are satisfied, and if they are, then you get a homomorphism. And because you can immediately see, like, the grading would be just looking at the assignments here, that the grading will be okay and would be preserved. And because we're using graph homomorphisms. So that's first. Because we're using graph homomorphisms, we have set grading. Then because it's proper, it's well defined. And you also check the path algebra relations. And proper is enough for path algebra relations. Then you want to have the first Kunz-Kruger relations, and for that you need this target bijectivity condition. And the last one is this regularity gives you the second Kunz-Kruger relation. Okay, so that's the whole proof. The idea. Okay, so let me go back to this question from the very beginning. Motivating question. So if I start with pushouts, and I use this functor, when do I get pullbacks? Right, so it's actually, I don't have any example like from the top of my head, but it's obvious that it won't always be the case. But you have to have some conditions. We'll see the theorem and the conditions, and then we can cook up examples very easily. Let me tell you what a pushout is. I mean, it's intuitively, it's very easy what a pushout would mean. So if I want to have a pushout of two graphs over a third graph, so what I look at, I just take pushouts in the sense of just set theory. That's first I check this construction. I do this construction where I have a pushout here and here, and then using universality of this construction, you get those maps. So the maps you get for free, right? But then you can ask yourself, but is this a pushout in the category of graph and graph homomorphisms? And then you prove that it is. So it is categorical pushout. Right?
But
My
i-
category-
sorry, but is it a push out in the category of
arbitrary graphs and arbitrary.
admissible?
No, no. So that's the whole issue. And last time I was giving this talk, I said something strange. Then you corrected me, Tomek, that I said that the category of admissible subgraph, right, the admissible category of graphs is not close with respect to pushouts, and this is not what I mean. It's wrong state. So what I wanted to say is that there's a warning here, right? So, and the Bourbaki in the book, there will be this Z sign that this construction takes you outside of admissible category. Right, so I don't know what the pushouts are in this category, but it's not this construction, because it's very easy, even already at the level of just sets. So forget about edges, just sets and finite to one maps. You can cook up a counterexample for that. Okay, so this is so this construction is not giving you the pushout. And so what we will do in this theorem, we will assume that you have a pushout, right? Because this is what this theorem was about, that our idea also from the very beginning about, like, imagine you have a pushout, is giving you a pullback. We're not thinking about existence of pushouts in that category. Okay, so with that. Oh, but first, to formulate the theorem, I have to talk about those breaking vertices, which are so problematic if you work with infinite graphs that have infinite emitters, because my graphs are arbitrary, right? So I can have infinite emitters, and I can have this situation, this very strange situations that I have a subgraph, right, and it emits outside of it. It emits infinitely many arrows, but only finitely many outside. And if I just kill this outside, right, I break one of the Kunz-Kruger relations. So you have to take care of those breaking vertices. And let me first tell you what they are. And I told you, in a sense, what they are. Just waving hands. So breaking vertices, I take an arbitrary graph and then a subset of the set of vertices H, and then I say that V in E0 is a breaking vertex with respect to H, if and only if. And now the following things it has to be outside of H. Okay. Then it has to emit infinitely many arrows, but only finitely many outside of H. So this.
I think you need strict inequality.
I was thinking about it while I was writing it down, and yeah, this is why I hesitated. But thank you. So you probably saw my hesitation. Came to the rescue. Okay, so that's the condition for being a breaking vertex, and then we have this notation that breaking vertices with respect to H are, we call this set BH.
Is there some intuition behind this name?
They're just breaking.
What does break at
Kind
its
of like
vertices?
the relations break. I don't know I don't know what was the intention of the author. So maybe someone knows, and I'll be happy to join. But what's happening is, right, you have this H. So imagine we're just talking about quotient graphs, right? So I have this. I want to have a map from a C-star algebra of a graph to a C-star algebra of a subgraph, right? Which we call the quotient graph. Now, if I have a vertex that is in this subgraph, it emits infinitely many things, but only finitely many outside, and then you kill only finitely many, right? Then you won't satisfy the second consecutive relation. So that's you have to think of a different quotient graph. So that's incorporating breaking vertices, and you can do it, and people do it in the literature, in the Lev algebra book, in many papers on graph system algebras. I don't know who was the first to come up with this.
Yeah, I mean, Mariusz was absolutely right. I mean, this is breaking the relation, but it's not our terminology, so don't take any responsibility. But this has a very nice picture, as Mariusz was explaining. The problem is with the second consecutive relation. If in your procedure of deleting these vertices and all edges ending in them, you turn a vertex which was not regular because it's infinite emitter. If by going to a subgraph, you turn it into a regular vertex, which is a finite emitter and not the sink, then, well, all of a sudden you have to impose the second type consecutive relations, which are not there. That's why this is what is being broken.
Yep. And also, so this, we wanted to avoid this when we were just like beginners and novices in the world of infinite graphs. We were just too scared, and we're like, oh, we don't want to talk about breaking vertices. And it turned out that the version of the theorem, including breaking vertices, is not that much harder in the end. So we were just scared for no reason. But okay, so let me go to the theorem now, because now we know the only thing I need for this theorem is this notation. So because I'll be using this notation, and there are some conditions for breaking vertices that have to be satisfied so that we get this push out to pullback theorem. Okay, the last theorem is this, that we start. So we assume we have a push out. So we assume that we have a push out of graphs. Oops, maybe I'll just write down just some arrows, not necessarily injective. So I have 4 graphs, and I'm assuming that this, and let me call them G, I, F. So let this be a push out in the admissible category of graph. Right, so I'm assuming all the morphisms are proper, satisfy direct with bijectivity, and they are regular. And I'm saying that then, and also, okay, so this was so the first theorem or the first result was about inverting the arrows, and now the additional assumptions are just for pullbacks to get the pullback. So we also assume this. So first of all, we need F to be injective. And then
F of G is of course symmetric. One of them.
course, yeah, you're right. You're right. Yeah, one of them, just F or G. In the push out, of course, you know that if in the push out, if F is injected, then this guy is injected, and it's the same if G is injected, then this. So we want one of the sides to be injected. So and then we have some more technical conditions. I don't want to make a mistake here. So first of all, is that if I restrict G 0, and this is about breaking vertices. All the remaining things are about breaking vertices. And I'll tell you a little bit about why they're important. This we want to be injective as well. If we restrict to the pre-image of breaking vertices with respect to the set E0 without F, the image of F0, we want to be injective on this as well. And then the last condition is that not only we want this to be injective, but we also want that this condition is satisfied. That this is inside breaking vertices. Okay, and oops, and then I run out of place, so I'll be running back and forth, but well, so then the induced maps, like the induced homomorphisms, now I look at the level of maybe Levitt algebras, because I was not talking about graph system algebras. So the induced maps at the level of Levitt-Path algebras. And this, when of course the maps are the ones that I just told you about. And this is a pullback of Z-graded algebras.
Is it one surjective?
Yes, because this one injectivity gives me a surjective map here, right? So if I have, because this, I'm pretty sure that I checked this, but Piotr, you can correct me if I'm wrong, but I think that if I have an injective admissible morphism, it's like a one-to-one correspondence again with those quotient graphs. So, I mean,
Yes.
these are really the same. Okay, so you can prove it when that when your morphism. Okay, so that's you can prove that if your admissible morphism is injective, then it has to be of this form of a quotient graph, and that we know. So we have to talk about gauge invariant ideals. So it's just the same. It's because then if it's surjective on the level of algebras, then it has to be a quotient by a gauge invariant ideal. So
It's surjective and equivariant or Z-graded.
as the grade. Yep. Okay, so we get this result. So this is the, again, not if and only if, we only know one way. And let me tell you a little bit about the conditions here. So those conditions are, so we know that we have this, so we have this push out of graphs, right? Then we use the previous result to write down a commutative diagram of algebras. Okay, and then there's a usual result that is used in the for pullbacks and all the time. And you can find it in the paper of Pedersen, for example, about pullbacks of C-star algebras. But it's a very general result about just abelian groups that you have conditions, and these are if and only if when a commutative diagram is a pullback. So then, okay, you look at the conditions and then you check condition after condition. Well, and then so it happens when you try to check all the conditions. These are the, let's say, our very general way to satisfy those conditions, right? So we're not saying this is the most general way to do it, but it gets it done, and it's the most general we have so far, and it generalizes all the results that were previously in the literature. And there's the conditions that you look at, and this is really connected to the fact that when you have breaking vertices, your hereditary saturated, your graded Z-graded ideals are not just classified by hereditary saturated subset. You have to look at those breaking vertices. And those conditions just make sure that if you write down the ideals, because it's a very nice way of writing down ideals in Levitt-Path algebras, you just have, it's a span of certain elements. And then you have to make sure that the containments, several containment of kernels and images works, because you're working with pushouts. And those two conditions gives you this. And I think I'm almost out of time. I'll say something more. Oh, okay. My last observation is, if you have it for Levitt-Path algebras, then you can complete it and use Alex Kirvasitu results, and then you get it for graph system algebras. So this you get for free. If you prove it for Levitt, then you have it for graph system algebras. Okay, and you just look at his theorem and you just check if all the conditions are satisfied, and they are. I didn't have time to write down. I don't remember the conditions, but this part is not the like a difficulty of this. So the difficulty was, and this is the fun part of the dealing with graphs, right? So the whole proof was just looking at the graphs, and if this path is there, is it here, and then looking at the graph at those breaking vertices and what happens with this, and the ideals are also written in terms of paths. So it's very combinatorial, and in the end you get the result about C-star algebra. So then, at least then I'm very happy. Okay, and I'll leave you with that. Thank you very much for your attention.
Any questions?
Yes, I
Yes,
have a
please.
question. So usually people ask about functors, about some properties of functors. Like for instance, do they transform finite colimits
Mhm.
into limits? And it is known that these finite colimits are generated in a sense by pushouts and coequalizers. So it would be nice to have this parallel theorem that this functor transforms coequalizers into equalizers.
That's actually,
This would mean that it transforms finite colimits into limits. And it would be very nice.
yeah, you're right. But, I never thought of it because this is, well, okay, recently I had to learn a lot of category theory working with Alex, but before that, I had, just push out pullbacks, that was enough for me. But thank you for that comment.
But if you look at this book on Levitt-Pav algebras, then all these questions about preserving limits are discussed at length for this covariant induction.
For the covariant, but like direct
a lot,
limits, but
yes.
not.
But I haven't never seen it. You see, when it comes to this contravariant induction, people always talk about subgraphs. It's always this, subgraphs injectives. It's something very, very special. So we wanted to go at least a little bit beyond it. So it's really about morphisms with some conditions, but it's not just about subgraphs. But of course, one could explore it in the same vein as for a covariant.
But I'm not sure if they talk about limits like in general. I think they only talk about direct limits of algebras. Yeah. In this covariant case, you can preserve the well, it's continuous with respect to taking direct limit. There's no, but for the covariant case, so what Piotr was talking about.
So yeah, can you show an example with breaking vertices and one with G non-injective? Is it related to projective spaces again?
I guess
So the graph of a projective space
yeah,
has no breaking vertices, or
but yeah, but there I don't think there are any breaking vertices there. But it will be something of like this example I can think of, like imagining of infinitely many here and only finitely here, and you want to kill this, so that right. So this vertex will be breaking because if we with respect to this subset, so it's called V and W.
so what is H? Only W, the single.
Yeah. So H will be just a single.
H would be the opposite one. That
Oh, the
precedes it,
H is
and
the
then-
other one. Thank you, Jack. Yeah, H is this. Sorry, H is this. Thank you. Exactly. Right. So you see if you want to fill this part, you get this problem because here you didn't have the relation, right? Because if you want to kill this vertex and everything that comes into it, you didn't have a relation here, and now it appears suddenly. So
does this appear in some example of Pull-Becker diagram? Or?
So I don't think so. Like the only thing we needed is this to take care with the breaking vertices is that they're just this annoying part that you have to take into account to have because one part is surjective, right? So this is where the breaking vertices come into account. So for on this, because if push out is one injective, so it means it's one surjective for pullback. And then if it's one surjective, you look at the ideal, right? Because if it's surjective, it's a quotient by the ideal. And then this ideal would be generated by some subsets. And you have to look at the breaking vertices. And then this is the part when you need it for the theorem. But nothing breaks for the pullback theorem because of breaking vertices.
Yeah, but what I was asking is if you have an example of a push-out diagram satisfying the condition of the theorem, a concrete example, which is not the one with the finitely many edges that we saw at the beginning.
Oh yeah,
Maybe with an injective G. Yeah.
Oh, so I was saying this that one type of examples that kind of, well, of course you can write down higher dimensional Podley spheres like this, right? And then higher dimensional, well, not Podley, but even spheres. you can do things like that, and then what will happen? No, but this is again finite. Maybe I'll think about something.
Even one example simply with a non-injective map.
Yeah, so
GS.
with non-injected maps, so whatever you do, you can just think, so okay, I have a graph here, right? I have some other graph here, and then in this graph I have this folding, right? And then I fold it here, and this will always be, and leave anything else untouched, and this will give you the type of amorphism. And then of course this part has to be injected now, right? So it will be here and it will be folded again in the push out. Well, so you can look at things like that. So this is not injected. So I don't know if it's giving you any. So you can draw anything else in this in the bulbs. Like, so this is then new kind of examples that we come up with. I don't have any other families of examples, but they should be easy to figure out, right?
Let me somehow continue answering Francesco's question. Yeah, we have to admit that this time our honest motivation was to get a result which would be at least in one dimension more general than that of Jack and his student. That is a very practical motivation. Unlike for the other pullback theorem, we just had these motivating examples and wanted to derive a theory. Here we just saw that, wait a second, I mean, this argument can be made more general. And when we make it more general, does it have some examples? Yes, it has examples, but they are kind of cooked up to work. But I don't have any non-commutative topology behind it to explain it's beautiful, it's needed, it's necessary, life is wrong without it. Okay. So that's why they are not popping up here, but this is what we are still working on. We want to explore examples for the theory. So somehow here it's the opposite direction. And
yeah, because somehow everything we have in non-commutative topology is finite and without breaking vertices.
Yes, yeah. But now, Jack and Mariusz, please correct me if I'm wrong, but the gist of what's the trouble with breaking vertices in this pullback construction. And it's embarrassing. I don't remember which way it is, but you see, imagine you are injected. Okay, I mean, we have this generalization; it works fine, and we have examples. So it's vacuous. But let's go back to the setting of two injected, and then you look at the intersection of graphs, and you put the intersection graph in one graph or the other, left or right. And now you can look at breaking vertices for one inclusion and breaking vertices for the other inclusion. And the condition for the pullback to work is, and I don't remember, it's this or it's contradiction, but the breaking vertex for one inclusion cannot be the breaking vertex for the other inclusion, something of that sort. Okay, that's the condition. You came up with the same condition in your paper. And then when it's satisfied, yes, you have this two surjective pullback. But you can get around it and you have these nice general conditions which generalize it and the pullback still works. Yeah.
Yes, it seems that it's what you're saying is correct, but I cannot just point out in this.
I just don't remember.
Yeah, I cannot just point out because these are the conditions and we're trying to make them like the most like efficient version. So you could of course write down more like this. You have actually equality here, but you only assume one inequality because the other one will follow. So I don't see it here, but I remember having this discussion with you. It seems that it's correct.
Are there any other questions?
Is it possible to generalize this to, for example, higher rank graph algebras? Because if we consider the example of a complex Higard projective space, then it is a higher rank graph algebra, and its pullback construction is also comes from tensor products of C-star algebras, which are also one graph. So the tensor products are K graphs as well. So would it be possible to do this in that case? Or?
Yeah, it's not only possible, or it's already done to some extent. So there's a paper by Aidan Sims. I'll assume Alex from GM as well. I don't know all the others, but there's a paper that they're hidden very like in some combinatorial journal that it's not without graph algebras in the title, but it's they assume something about, so it's not for all. It's they have some assumptions like k-aligned. Is that the name? I'm not really fluent with higher rank graphs. So of course for us it's part of the project, right? To do this for a higher rank graph. So if you're interested in that, we're more than happy to talk about this. But there are already some results that if you look at one graphs, it's very narrow. Like our results for one graphs is much more general than what you get from this higher rank graph. So there's a possibility to generalize it a lot. And they needed this pullback for something else. So they're interested in some other results. But along the way, they proved it just the same way you always prove it. So they had some, but they were not looking at push-outs, but something that you can understand as a push-out. So from our perspective as well. But they got some conditions. So of course, all maps were surjective. They had some conditions for those subgraphs, high-rank subgraphs. And out of it, you can get a pullback of high-rank graph system algebras.
But this big restriction that they have is that when you specialize the results to graphs, just one graphs, then they require that there are no sinks. And for us, that's unacceptable. We won't tap into algebra. We want balls. Thank you.
Also, I have a comment and a question, I guess. I guess the comment is that, again, it seems like this homomorphism that you find between the graph algebras preserve the diagonal. So again, should be interesting to look what happens to the boundary path space. Probably there's some kind of continuous function there that maybe implements the homomorphism. And the question is, does anyone look at a category where instead of looking at objects only graphs, you look at pair where there's a graph and a subset of regular vertices, and then you build the relative cone algebras?
So was that Jack, right? You did some of that, or yeah, exactly. So if you look at Jackson and Sam paper that I was talking about at the very beginning, they do this result, and if you specialize it to what we do, it gives you the same conditions, but with the only kind of abstract that we have is that our morphisms are more general, right? So the first part of the theorem, the first result is more general, but this theorem, you can find in their results the same kind of conditions or equivalent conditions.
Other questions or comments?
I have a quick comment, and we are on the right slide. So I'd like to draw your attention to this assumption number one, that F is injective. So Mariusz bypassed one step, namely on the way from push-out to pullback, there is the push-out of a set of finite paths. Look at finite paths as sets, okay? And you are wondering what are the requirements for push-outs of graphs so that they really induce, and this is of course a covariant induction, push-out of the sets of finite paths. And here you have quite severe restrictions, okay? But coming back to this injectivity, you see, we must be proper. We must be finite to one. So we have this concept of a push out in the category of graphs and graph homomorphisms, okay? We assume our F and G's to be finite to one, proper, and then you can cook up a nice, it's not trivial, it's a very nice counterexample that the other maps are not finite to one. I mean, push-outs exist in this category, so these morphisms exist, but they are no longer finite to one. And in order to ensure that we are always finite to one of the assumptions we're forced to make, I mean, maybe there is another solution, but this is a solution which makes us happy because we want to be one injective anyway, is that if one of these maps is injective and the other one is finite to one, that the other guys, well, of course, IF is again injective, but IE is again finite to one. And this is not true if you assume F and G finite to one. Okay. So that's where we need it, this injectivity.
Are there any questions or comments from the online participants?
No, I don't see any raised hands.
But yeah, maybe somebody didn't raise a hand, but wants to say something.
I don't see anything in the chat as well, I think so, no.
Okay, Piotr, you had one more comment? No? Okay, well, let's think. We adjourn at 3. We adjourn. Start up again.
How do I stop recording? So how do I, this is stop share now, more, stop recording, okay.